Welcome to Transconductance Amplifiers, Part 2. Part 2 is about MOSFETs. So MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Higher gate input resistance than a JFET. It's about 10 times higher. So JFETs are about 1 to 5 meg ohms. These are like 10 to 20 meg ohms. Super high input resistance on the gate, but that makes them static sensitive. Right? They can handle higher drain currents than a JFET. So you can kind of think of a JFET as a small signal transistor, like this one here, and then a MOSFET as a power transistor, like this one. They have a lower drain source voltage compared to a BJTs. MOSFETs in digital logic, we see them all the time. They're smaller physical die size than a BJT, which allows more transistors in an IC. They're faster switching than a BJT also. 2N3904 is an example of a bipolar junction transistor that we used in the lab. They're lower power because VN controls I out. So you don't need a current on the input to control it. You just need a voltage. You need a voltage on a very high input resistance, which means there's hardly any current or power used to turn these off and on. CMOS is an example of a digital logic series, a complementary metal oxide semiconductor, and they're the 4000 series. Another one is the 74HC or the 74C series of digital logic, and they're high-speed CMOS or just regular speed CMOS. There's two types of modes that MOSFETs are used in. Well, there's two lines, if you want to say. One is called depletion mode and one is enhanced mode. Depletion mode, rarely used. I don't think I've ever used a depletion mode MOSFET. And what's interesting is this device is normally on. And then what you do is you apply a negative voltage bias on the gate to turn it off. So you can see right away that doesn't make sense. So we don't really use it too often. Enhanced mode is the one that we use, is most commonly used. The device is normally off, like a regular transistor is normally off. And then what you do is you put a positive voltage bias on the gate, turns it on. These are the depletion mode symbols. Basically, they're just like a JFET. You have your drain, gate, and source. And we have an interesting symbol inside here. This is just one device with three leads on it like this, the gain, drain, and source. And inside, in the past, I've seen students get confused because they think that they have to hook up a diode to the circuit. There's no diode required. It's one device with this crazy looking symbol. One of the things you want to notice is, see the center bar down the middle here? It's solid. Solid indicates it's depletion mode. There's an N-channel devices. This is the N-channel that we use. This is equivalent to NPN. And then there's P-channel MOSFETs, which are used with negative power supplies. Enhanced mode, this is the one that's used all the time. I'd say 90% of the time is enhanced mode. And again, we're describing one device with the symbol. We have our gate, drain, and source. And then we have this crazy symbol in the middle, which just describes what a enhanced MOSFET looks like. And interesting is the arrow points in for N channel, which we use with positive supply. So it's the opposite than a transistor. I always get confused. Literally, I always get confused. I always have to double check on it. But if you look at the center bar here, here's the center bar. It's a dotted line, right? And that's how we know that this is enhanced mode. This is the P channel. The P channel is used for negative power supply, so we don't see that too often. MOSFETs as a digital switch. MOSFETs make great digital switches. The enhanced N channel is the most common used, and it's equivalent to an NPN transistor. A small input voltage called VGS between the gate and the source controls the drain source, right? So if we put a voltage on here, and typically, so if you put at least 8 volts in, this will switch hard and that will turn on, right? So I've always used 8 volts. And if you actually look the specs for different versions of MOSFETs, you find out that some are 4.5 volts threshold, some are 6 volts, some are 7 volts. And if you go with 8 volts, you're guaranteed this thing's going to turn on nice and hard. Okay, so the voltage that this will turn on is called VGSTH, for voltage gate source threshold. MOSFET's drain source resistance is called RDS. Right? So when a MOSFET turns on, the drain source junction from the drain to the source here, and when it turns on, it's like a switch closing. What happens is it has the characteristics of being a resistor. So it looks like a resistor, and it looks like a very low value resistor, less than 1 ohm. Right? Low resistance is a good thing. So if we compare a BJT power transistor to a MOSFET. So here's a very typical BJT transistor, a 2N3055. It's a power transistor used all over the place. It's kind of like the 2N3904 is the one that's used for everything as testing for small signal. 2N3055 is very common in the power. And it has a spec of VCE sat, so that's our saturation voltage when the transistor is turned on. It'll have a voltage of 1.1 volt across it when you're running 4 amps through the transistor. So at 4 amps, it's going to have a VCE sat of 1.1 volt. Interesting with BJT transistors is that the more current, the larger VCE sat is going to be. Right? So if we calculate the power loss through this transistor, it's just basically the power is equal to voltage times current. We get 1.1 volts times 4 amps gives us 4.4 watts of heat will be dissipated on this transistor here. We need a heat sink on it. Now if we pick up a MOSFET and we look at its spec for RDS on, first thing we'll find out is a MOSFET is a smaller transistor package. It's a TO220, right? But it has an RDS on of only 27 milliohms or 0.027 ohms at 4 amps. If we run it through our power formula, which is I squared R, we get 4 amps times 4 amps times 0.027 ohms is equal to 0.432 watts. Hardly anything. We don't even need a heatsink. MOSFET is a digital switch review. So we require a minimum gate source voltage of VGS threshold to turn on. When turned on, the drain source junction acts like a resistor, RDS on. A MOSFET is very efficient compared to a BJT power transistor. Dissipates 1/10 the wattage as heat. Doesn't even need a heatsink. Switches much faster than a BJT. Sometimes it switches too fast. I've actually had circuits where I've actually had to slow down the turning time of a MOSFET so the rest of the circuit could catch up to it. I can handle insane amount of current, 25 amps to 80 amps. So ID max can handle 25 amps to 80 amps. So how does that compare with a BJT power transistor? They can only handle about 5 amps to 20 amps maximum. If we look at the specifications for a MOSFET, we'll see that very first one is VGS TH, which is our gate source threshold voltage, and that's the voltage to trigger the MOSFET to switch it on. It takes about 8 volts, kind of a rule of thumb. You say 8 volts, man, you're safe there. We also have the gate source maximum voltage, VGS max, and that's basically the maximum gate source voltage that you can put on the gate before you'll damage it, typically about plus or minus 20 volts. RDS on is the drain source resistance when on. Typically it's less than 1 ohm. We can get down in the milliohms, 27 milliohms, 20 milliohms, and that. A VDS max is the maximum drain source voltage, and that's the voltage between the drain and source. Typically it's greater than 100. You can get these at 50 volts, 100 volts, 200 volts, 500, 600 volts, etc. ID max is the maximum drain current, typically 25 amps to 80 amps or larger. They can handle lots of current. Here's a MOSFET switching example we're going to do. It looks like a complex circuit. We're going to walk our way through. So very first thing, we're going to look at point A. Point A is R1, R2 voltage divider with our base emitter junction. So this is just a series circuit that's going this way. And we're going to take a look at it with switch 1 open. If it's switch 1 open, we've got our 12 volts here. 12 volts comes down here. And then we have a series resistor, another series resistor, and a base emitter junction. So we're going to have current flowing, so we're going to drop 0.7 volts here. We start with 12. 12 minus 0.7 gives us 11.3. Divide that by 2, because now we just have 11.3 across 2 resistors, the same value. So 11.3 divided by 2 is what, 5.65? And so this will be 5.65, and then we add 0.7, we'll get our 6.35 volts here. So we got 6.35 volts here, we got a voltage here. Since we got a current flowing through the base, that means this transistor is going to turn on. It's going to act like a switch, turn on, and we'll get 0.2 volts here approximately. So regardless of what this voltage is, this is going to be pulled down to 0.2, and we'll get a current flowing here, so we get 0.2. 0.2 volts is going to go to the gate. The gate that's not enough to turn on our MOSFET here. So this MOSFET is going to act like an open switch. So what we'll find out is we got 0.2 volts here. This LED will turn on because we're going to get current flowing through the 1K, through the LED, through the transistor to ground. This LED will turn off because this Q2 is acting like an open switch, so we won't have any current flowing. So let's take a look at the second condition when switch 1 is closed. So I've closed switch 1, which means we've grounded this point here, point A, so now we get 0 volts here. If we have 0 volts here, there's no current flowing, we're going to get 0 volts at Q1. Q1 gets 0 volts, which means that Q1 is going to be turned off and acting like an open switch. R3, D1, and R5 determine the gate voltage. Because this is acting as an open switch, it's like it's not even in the picture. So we'll just look at these three devices, and they're in a series circuit. The gate resistance for a MOSFET is very high. It's going to be like 10 megohms. So 10 megohms is so large we can ignore it. So let's take a look at what we have here. The LED typical forward voltage is about 1.8 volts. So if I start with 12 volts and subtract 1.8, I'll get about 11.2 volts. Now, I have 11.2 volts across a resistor of 1K and another resistor of 100K. This is about 1% the size of this. So if I say this drops 1% of the voltage, we started with 11.2, 1% of that is 0.1. We're going to get about 11.1 volts over this R5. And that's what the gate voltage will be here, 11.1 approximately. 11.1 volts is enough to turn on our MOSFET Q2. So it's going to act like an open switch. When it closes, it's going to have a resistance of about at 0.1 ohm, very, very low resistance, and we're going to get current flowing. The resistance is so low here that in this circuit, we have a 1000 ohm resistor here. We got 0.1. There's going to be almost no voltage drop across here. So what we'll find is that we will have current flowing through here. The result is we have this switch is open, so we're going to have current flowing through here. This one, if we look at the path, it goes through a 1K to a 1.8K to a 100K. 100K is not going to give enough current to light this LED. There will be current flowing through, but it'll be so dim we probably won't see it. Having said that, I have seen that some of the super bright LEDs will glow dimly even if we put a 100K resistor in series. So if we said 12 volts divided by 100K, we're looking at like, 1K is 12 milliamps, 10K is 1.2 milliamps, 100K is 120 microamps. So some of the super bright LEDs will even light up with 120 microamps in it. So that concludes this section on part 2 on MOSFETs.